Someone once did the math. If humanity used all its steel, we could build a tower all the way to the moon. But at a certain height, the building would start crushing itself under its own weight. Go higher, and the wind isn't just blowing on you, it's slicing you. How bad does it get? At the top of the 828-meter Burj Khalifa, the entire tower sways side to side by 1.5 meters. That's not an accident. The engineers designed it that way on purpose, because if it didn't sway, it would have snapped long ago. But the thing that shuts up every architect isn't the wind. It isn't gravity, it's your own body. Above 19 kilometers in altitude, your blood will boil at body temperature. No external force needed. It just boils. So how high can humans really build? The answer is 100 times crazier than you think. Let's start with the Burj Khalifa. When construction began on this 828-meter giant, nearly every seasoned architect said it was doomed. Sandstorms in the desert made the foundation dangerously unstable. Builders had to drive nearly 200 concrete piles into the ground, each 50 meters long, just to keep the monster from slowly sinking into the earth under its own weight. But the biggest threat wasn't below ground, it was at the top. Above 500 meters, wind speeds rival hurricanes. If the tower were perfectly rigid, the first big gust would split it in half. The engineer's solution was unexpected. They shaped the tower like a 3-petal flower. Looking straight down, the Burj's cross-section resembles a staggered floral pattern. That's not for looks, it's to shred the wind. When airflow hits that irregular step shape, it breaks into a swarm of chaotic eddies. The wind loses its destructive power. But even then, there's a hidden limit rarely mentioned: the steel cables in the elevator. At 600 meters, the cables begin to stretch and tear under their own weight. That's why in supertall skyscrapers, you can never take a single elevator to the top, you have to transfer midway. And for even taller buildings, this problem has no solution. So what if we don't build a slender tower? What if we build something as wide as a mountain? In 1995, Japan's population was exploding. Land was critically scarce. A group of wild designers proposed a plan called Exceed 4000, a steel pyramid 4 kilometers high, capable of housing 1 million people in comfort, with parks, shopping malls, and its own weather control system. Even artificial rain inside the dome. Sounded flawless. But when engineers ran the numbers, the room went silent. The base would need to be 6 kilometers wide. Its total weight would punch a crater straight into the Earth's crust. The whole structure would slowly sink into the ground like a massive stone. The project died right there. If concrete and steel aren't enough, can we swap in a stronger material? In 2004, 2 scientists used a piece of ordinary graphite and a roll of tape to peel off a layer just 1 atom thick. That's graphene. Then they rolled it into carbon nanotubes, 200 times stronger than the best steel, at 1/6 the weight. The world went berserk. Some declared that within 5 years, all buildings would be rebuilt with graphene. Others claimed the military had already used it for invisible armor. But reality is brutal. Scientists can still only grow nanotubes a few centimeters long in the lab. The moment you try to weave them into a rope or a beam, their strength collapses. And a kilogram of nanotubes costs astronomically more than gold mass production is impossible. Material science failing. Is there a way to make a building that doesn't rely on materials to support its own weight at all? Yes. It's called a space fountain. Imagine a water hose shooting straight up, holding a ping pong ball on the jet. The ball hovers. As long as the water flows, the ball won't fall. A space fountain works exactly like that. Inside the tower is a vacuum tube. Millions of magnetic capsules shoot upward at tremendous speed, bounce off an electromagnetic coil at the top, and are flung back down. That constant impact holds the entire tower in the air. No heavy walls, no foundation. Theoretical height, over 20 kilometers. But it has one fatal flaw that makes your spine tingle: a power failure. If the electricity cuts, that 20-kilometer tower will collapse in minutes, flattening everything for hundreds of kilometers around. Even if you solve all material and structural problems, there's one final barrier: your own body. In the 19th century, balloon pilots ascending to 8 kilometers began to feel inexplicably happy. They wanted to sing. To laugh then, they quietly lost consciousness. Many never woke up. The oxygen level at that altitude is actually the same as at sea level, but the air pressure is so low that the lungs can't push oxygen into the blood. People just fall asleep without a sound. And at 19 kilometers lies a line called the Armstrong Limit. Cross it and the pressure is so low that all the fluids in your body will boil at normal body temperature 36°C. Blood and bodily fluids together. That's not a metaphor. Any ultra-tall building would have to be sealed and pressurized like a submarine. A single broken window would trigger a catastrophic chain reaction. So what if we flip the whole idea? Instead of building from the ground up, we hang from space down. That's the space elevator. Anchor a satellite in geostationary orbit at 36,000 kilometers. Lower a cable from the satellite all the way down to the equator on Earth. Cargo and passengers ride up and down smoothly. No rockets, no fuel. A direct path to the stars. And the ultimate vision of human engineering is a complete orbital ring encircling the entire Earth, suspended hundreds of kilometers high, connected to the ground by thousands of elevator cables. Along that ring, cargo could reach any point on the planet in hours. We started with a building afraid of the wind. And we ended with an idea to rope down the entire planet. How high can humanity build? There's never been an end to that question. As long as we haven't stopped, the limit is always just ahead.